All right, let's dive in. Today, we're putting on our hard hats and becoming mathematical architects. Why? Because we're tackling rational functions. And these things, well, they're basically the blueprints for some of the wildest, most surprising graphs you'll ever see in math. So let's get to it. So check this out. At first glance, it just looks like a curve, right? But look closer, it's broken into pieces. And it's like there are these invisible walls that the graph gets super close to, but somehow it never actually touches them. How does that even happen? How can a simple fraction create a graph with these bizarre gaps and boundaries? Well, that's exactly what we're going to figure out.
The secret, as you might have guessed, is all in the blueprint, the rational function itself. And honestly, it's a pretty simple idea. It's just one polynomial sitting on top of another one, a fraction. But here's the cool part. Every single piece of that fraction is an instruction, a little command telling us exactly how to build our graph.
Okay, so where do we even begin with this blueprint? Well, let's start with the most dramatic parts, the breaks. The spots where the graph just stops. We're going to read this blueprint to find out exactly where those breaks happen and, just as importantly, what kind of breaks they are. And what's really cool is that the secret to all these breaks is hiding in plain sight. It's all in the denominator, the bottom part of our fraction. Think about it. What's the one unbreakable rule in math? You can't divide by 0. So it makes sense, right? Any x value that makes that denominator turn into a 0 has to create some kind of break in our graph. It's a mathematical dead end.
But here's where it gets interesting. Not all breaks are created equal. You've got two main types. The first is a vertical asymptote. This is like a giant invisible wall. The graph runs right up to it, but it can never, ever cross it. Then you have something called a hole. A hole is way more subtle. It's like the architect drew a beautiful, continuous line and then just erased one single tiny point, a deliberate gap.
So how do you find these invisible walls in the blueprint? It's actually pretty straightforward. First, you've got to factor both the top and the bottom of your fraction. Then you look for any factor in the denominator that doesn't get canceled out by something on top. That's your guy. Set that factor equal to 0, solve for x, and bam, you've found the exact location of your wall. Okay, what about the holes? Those little gaps? Well, those come from the factors that do cancel out. When you have the same factor on the top and the bottom. Finding the x location is the same deal. Set that canceled factor to 0. But, and this is super important, to find the y coordinate of the hole, you have to plug that x value back into the simplified function, the one you get after you've canceled the factors out. All right, let's keep going. We've found the breaks in our structure, the walls, and the gaps. Now we need to look at the bigger picture. We need to map out the boundaries. What does this graph do when it stretches way out to the edges, as it heads off towards infinity?
These boundaries are what we call horizontal asymptotes. I like to think of them as fences that guide the graph's end behavior. Now, here's a key difference. While a graph will never cross a vertical asymptote, it can sometimes cross a horizontal one. The main job of the horizontal asymptote is just to tell us where the graph is going to level off as x gets incredibly big or incredibly small.
So, how do we find these fences? Turns out, it's just a simple comparison game. All you have to do is look at the degrees of the polynomials, the highest exponent you can find. We'll call the degree of the numerator n and the degree of the denominator m. That's it. And comparing n and m gives us 3 simple rules. It's that easy. Rule 1. If the denominator's degree is bigger, we call this bottom heavy. The asymptote is always y equals 0, the x-axis itself. Rule 2. If the degrees are the same, the asymptote is a line at y equals the ratio of the leading coefficients. That's just the numbers in front of the highest power terms. And rule 3. If the numerator's degree is bigger, or top-heavy, then there's no horizontal asymptote at all. But wait, that top-heavy case has a really cool plot twist. If the numerator's degree is exactly 1 bigger than the denominator's, something special happens. We don't get a horizontal fence. No, we get a diagonal one. It's called a slant asymptote, and it acts as a tilted guideline for the graph. To find its exact equation, you use a technique called polynomial long division, which is a whole other adventure. Okay, we've got all our rules. We know how to find the walls, the gaps, and the fences, all just by reading the blueprint. So what's next? Let's do it. Let's put everything we've learned together and actually build a graph, step by step, from scratch. So here's our blueprint for today. Yeah, I know, it might look a little intimidating at first, but don't worry, we have a clear, step-by-step plan that's going to turn this mess of symbols into a beautiful, clear picture.
Step 1, and this is always step 1, we factor everything. Break it down into its simplest parts. This is how we reveal the real building blocks we're working with. And wait a second, do you see that? We've got an x minus 1 on the top and on the bottom. That's going to be important.
And since those x minus 1 factors cancel each other out, what does that mean? Yep, we've got a hole. To find where, we just set x minus 1 equal to 0, which gives us x equals 1. Then we plug that 1 into our simplified function, and out pops y equals 5. So let's go ahead and put an open circle right there on our graph at the point 1, 5.
Okay, next up, what's left in the denominator after we canceled everything? We've got that x plus 2 factor just hanging out. Since it didn't cancel, this is our vertical asymptote, our big invisible wall. We set x plus 2 equal to 0, which means our wall is at x equals -2. Let's get that dotted line drawn in.
All right, time to figure out the boundaries. We look back at the original equation. The degree of the top is 2, and the degree of the bottom is also 2. Hey, they're equal. That means we use our equal degrees rule. We just take the ratio of the leading coefficients, which is 3 divided by 1. So, our horizontal fence goes right at y equals 3.
And just like that, look at that. The entire framework for our graph is in place. We've got our walls, our fences, even our little gap. The only thing left to do is sketch in the actual curve. We know it has to hug those asymptotes as guides and pass right through where that hole is. Let's draw it in.
So what's the big idea here? It's that the equation was never just a jumble of letters and numbers. It was a blueprint all along, a detailed set of instructions. Every single factor, every single degree, it was all telling us exactly how to build this thing, from the ground up.
It really makes you think, doesn't it? If a simple-looking fraction can hide a blueprint for a structure this intricate and, well, this cool, just imagine what other incredible designs are waiting to be found, hidden deep inside the language of math. Thanks so much for joining me.